Okay, so we'll continue on here. So now we're going to talk about the CCE test for basically for all fluids with gas-oil ratios greater than about 1,500 to 2,000. It would be 300-ish to 400 standard cubic meters.
But it's also for oils, right?
Yeah, so this is going to be oils transitioning into gas condensates. So the typical transition GOR from oil to gas is around 3,500 cubic feet per barrel, about 700 cubic meters per cubic meter. I mean, it's not an exact transition from being an oil to being a gas, but in that range, between 6 and 800 cubic meters per cubic meter, it typically goes from being an oil to gas condensate as a general rule. But what happens in these systems is that the fluid itself, as a single phase, even if it's an oil with a bubble point, it's still a very compressible oil. So now the compressibility, because there's so much gas in solution in the oil, its compressibility is relatively high. And the result of that is the single phase pressure volume relationship is not a flat straight line, it's kind of a curving upward straight line. So what I'll do is I'll kind of show you how their behavior would look in a blind PVT cell. If we just look at total volume, it's hard for me to draw from right to left here, so I'm going to draw from left to right. Of course, at low enough pressure, it's going to be two-phase, and what you're going to see is that it's going to be looking something like this. It looks relatively continuous, the pressure-volume relationship, and there's no clear break in. So we don't know where it's going from single phase to two phase. That's the problem. And if we sketch down below here the total system compressibility, as we did before, basically what you get is you've got something coming down like this. And then if you had really accurate pressure volume information, you would actually see a slight discontinuity, but it wouldn't be enough to, it would be difficult to see. So there is still, and now I'm identifying the saturation pressure being here, but you can't really see it from the pressure volume curve. So in these systems, we have to visually observe the two phases appearing. Okay, so in the second type of test, we have to use a visual PVT cell. Okay, and you think, oh God, this is not going to be easy. I'm going to have to get my magnifying glass or my microscope out, looking for that first little bubble of gas to appear, right? And you know, I've got the whole cell to look at. I've got a window now, and I'm going to have to go looking around. Where's that damn bubble showing up? Or maybe it's a condensate, and there's a little drop of liquid that condenses and rolls down the side. But you know, so it doesn't work that way. In general, you don't look for that first little drop or bubble. Instead, what we do is that we measure, as a function of pressure, of course, we measure total volume, and we look for the liquid volume. Okay? Of course, by difference, you have the gas. And for an oil, I'm gonna draw the oil volume in the case so basically you won't know what it is above the saturation pressure, right? But if it's an oil system, I'll do that in green. What it'll look like is this. when you get right here, you'll get this measurement there. That's the oil volume, together with that measurement there, which is the total volume. So 10% of the cell is gas, 9% of the cell is oil. That's not a bubble. Okay? And then this will drop down probably quickly, and it'll flatten out something like this. Okay? That's what oil data would look like. This is the oil volume. And of course the difference between here and here, the total volume and the oil volume, is what? That's our gas volume. This is total volume and oil volume. So to identify what is exactly the bubble point, you have to kind of blow up right around here. You have to kind of blow that up and do an assessment of those volumes. But you're going to be extrapolating to get that bubble point. You're going to be extrapolating this volume, that volume, maybe this volume, these three volumes. You're going to do something, and you're going to be extrapolating that to where it crosses the total volume curve. And because it can be quite nonlinear, well, it'll be, it won't be too bad, but you'll basically identify that, okay, that's my bubble point volume there. So what you're seeing here is that you're still getting single phase volumes that giving you single phase densities. This is an oil, so we're getting the densities of oil greater than the bubble point, equal to. And you're getting the relative oil volumes. You're getting the gas and oil volumes as a function of pressure. So the phase amounts. Speak up, please. Yeah, so why is the oil volume continuously shrinking, is what we call it. It's because gas continues, generally it's monotonically, it keeps the oil, as you go to lower pressure, more gas comes out of solution. When gas comes out of solution, the oil volume shrinks. That's right.
But how do you put this, like, okay, you're doing this test from the pressure close to the reservoir one, for example, or whatever you're interested, down to the surface pressure, like standard condition?
Well, typically you have to stop where this volume here is typically around 4 times what you start with.
Okay.
It's usually 4 or 5 times.
But the point is to fill this cell with this oil, with dissolved gas. You have oil in surface conditions already. So how are you doing it? Like you have oil, singles fill this cell.
How do you fill the cell? Okay.
Yeah, like exactly. And how you keep this condition that the pressure haven't been like dropped before.
Right. Yeah. The thing is this, that I didn't tell you how the cells are charged. Okay. Filled. The cells filled. If you have an MDT type sample, it's at reservoir pressure and temperature. So you can pressurize it to 1,000 bar. Make sure it's single phase. Likewise, a bottom hole, cased hole, traditional bottom hole sample, you can also make sure it's single phase, charge it directly into the PVT cell. So for the bottom hole samples, you can make sure that the sample container is single phase. You then push the fluid into the PVT cell. If you have separator samples, you have to fill it first with the one separator gas, then you fill it with the separator oil in the correct amount. That's why that gas-oil ratio we talked about during sampling was an important ratio. That's why the lab needs to know what the ratio is. It needs to know how much separator gas to add to the PVT cell, how much separator oil to add to the PVT cell. So that's the way it's done. Then they pressurize the system way up to here, maybe to initial some very high pressure, maybe the max pressure the cell will tolerate, to make sure they'll shake the cell to make sure that any two phases go back into single phase before they start the pressure depletion. This is the first point, the second point, third point, and so forth. Each time they come to a new pressure, they have to shake the cell, physically agitate it. Maybe they have a stirrer inside, a magnetic stirrer, to make sure that there's equilibrium achieved. It's a little bit like it's like your Fortis, your soda bottle. You buy the bottle of carbonated water, right? You open the cap. You're at 1 atmosphere, right? Well, what you know is that if you let it sit there for, I don't know, a couple hours or whatever, all that CO2 is going to finally go out and you're going to have dead water. Okay? But it doesn't happen like that. No? You have to shake it. If you shake it, you open the cap. You shake it, you open the cap. You can get it down to maybe within 10 seconds. You know, about the time it takes to do the Rubik's Cube or whatever it's called. Yeah. Do you know what the world record is? It's not very. It's pretty damn fast. So you can probably do that faster than you can get all the CO2 out of the water, because you have to shake it, open, shake it, open. So the same thing's going on in the lab. They have to shake. You know, they lower the pressure. They have to shake the cell until the pressure stabilizes. Yeah. Okay, but they see the total volume, and then they see that, oh, now I see an interface.
Yeah, but that's visual. For example, if you have an instrument, it's measuring the level of the oil inside the tank.
That's right.
That will be showing you that the level is increasing until some point when at the low pressure, when the level is starting to increase, then that's only the level of the oil, not the gas.
Yeah.
Then you will get
Well, the total volume, I think, is measured independently. It's basically the pump. You know how much you're basically taking out, and you know how much volume has changed from the pump volume. That's the total volume. And then you basically look inside the cell and see a physical volume of oil. Some labs, and there's a few of them that are notorious for this, some labs have a problem with consistency. Okay, that there's a calibration error in the liquid volume. In other words, if they could see just the liquid volume filling everything, they wouldn't get the correct total volume. So you can have this. The oil volume is an independent measurement, and it needs to really be calibrated accurately to make sure that it's giving you the correct physical number of cc's of oil in the cell. So I'm not quite sure what you're asking, because you basically have this one measurement from the pump of the total volume. You have the visual measurement of the oil volume in the cell from another piece of data.
so you're continuously doing this. It's not a batch process.
Yeah, each of these, you've got 1, 2, 3, 4, 5 pressures, 6, 7, 8, 9, 10. You might have 20 of these pressures. Each time you have to shake it, equilibrate it. Yeah.
But once you shake it, then the measurement that you do is PV pressure and volume.
Yeah.
With the closed system.
That's right. It's a pressure volume for a closed system. That's right. But if you only look at that data, you get the blue curve and you don't know what's going on inside.
But that's what I mean. That if you have a blind cell, for example,
Yeah.
inside it you have a level indicator for the
Oh, a level indicator, like a sonic or something.
like that.
There's all sorts of good ideas out there, different. But I think that the laboratories, some still use mercury. Don't use pistons even. So I mean, you have all sorts of types of devices. Maybe somebody uses a sonic detector. Yeah, I don't know.
So to make it clear, total volume is not observed in the chamber. We're checking only the oil volume, and total volume is like calculated by tons.
Yeah, and they're independent measurements. And if there's an inconsistency, and we see it sometimes, then the reported data are erroneous, if you will. So. Finn Haven's not here, but if you know, his dad identified a fairly serious systematic problem of this particular thing in one of the Gulf of Mexico laboratories when we were doing some studies there a few years back, and a very systematic change in the reported oil volumes, just a constant, basically a constant factor, brought everything into consistency. And after 3 or 4 laboratory reports looking at that data, we identified this has to be a systematic error. They went into the lab checked their procedures and found that there was some calibration error with the liquid volume measurements. Okay, so now let's take a look and see, what if we have a gas and it starts condensing out a liquid? What will it look like? Well, the blue curve will look very much the same. Very much the same. But now I'm going to use black for condensate. Okay. And here, basically, you'll see nothing of liquid. You don't see any kind of two-phase. But here what you'll see is that you'll see a little bit of liquid, a little bit of liquid. Well, the magnitude on the y-axis may not be. Let me go back. And then if you go to low enough pressure, it starts dropping again. Okay? It's not a very good picture because the scale is so terrible. But basically you start seeing condensate here the first time. You reach a maximum in the amount of oil that you see, and then it starts decreasing again. So that's your first observation of a liquid. And again, in order to find out what is the dew point, you have to kind of take and blow up these few points, and you have to extrapolate. So you see, you might extrapolate back here. Maybe you had the last pressure here. You might extrapolate there, or it could be there, or it could be there. It could be any of these, anywhere between, you know, where you didn't see anything two-phase to where you saw something two-phase. So basically, the dew point can be anywhere from here to here in reality. Because that oil volume, it may grow quickly or it may grow very slowly. I'm going to blow this up for you just so you can get a... Now we're just looking at the oil volume versus pressure. We have 0 here, 0 here, 0 here. Now this is going to be like, you know, 10% or 10 cc's or something. And now you're going to start seeing that it may go straight up, reach the maximum, goes back down, like that. In this case, it's fairly easy to kind of do an extrapolation. You know, you could extrapolate it down here, or you might extrapolate it up here. So So this is kind of the uncertainty in the dew point pressure. Here you didn't see anything. Here you saw this. Now sometimes the lab, this lab technician either needs new glasses, needs to take her glasses off and clean them, has been drinking too much the night before, is on illegal substances, or just altogether had a bad day. And they might start saying that, oh, you know, something looks foggy to me here and here. Here I don't see anything. I wasn't looking. Okay, and they kind of say, well, they say trace. And a trace is something that's so small you can't quantify it, but you think you see something. You know? It's like the goalkeeper last night in the big football game. You thought the guy was going to kick it that way and the ball went that way. You know, it wasn't just... So sometimes it's real, sometimes it's a mistake. It can be real. There can be actually a few of these little heavy molecules just dropping out, but they don't form together. They form kind of around. There's not enough of them that you can quantify it. So there is something going on. Mother Nature is dropping some of those heavy components out of the gas into a liquid phase. Sometimes it's real, sometimes it's not. If that's the case, the dew point could be anywhere from here out to here, right? Because what is the dew point? The dew point is the pressure where Mother Nature starts kicking the butts out of the heavy components out of the gas and forming liquid. Okay? We don't want you here anymore. So the heavy components have to be forming a liquid phase. But they don't have enough of them that they can get together and, you know, have a party. They're kind of condensed out on different parts of the glass window, maybe parts you don't see. And then finally, after you get enough of them, they condense together and you can actually make measurements of them. Okay? So what you can see here is that the dew point, in some cases, may have a significant uncertainty to its magnitude. It may be 1 bar. It may be, there's one case in Norway, there's one case of the Vala field, where I've seen it be as much as 100 bar. Okay. They had the two laboratories. The one laboratory was Core Labs, and the other was the French lab. I don't know if it's Flow Patrol or the Total lab. The same fluid system was sent to both labs. Core Lab came back with a very clear, straight down. It was a dew point 420 bar. The French laboratory had this tail. It was more than a trace. It showed, but not very much, all the way out to 650 bar. Actually, it was 200, right 100, but the Vala was a case where we had a difference between one lab and the 250 bar difference. So, yeah. So anyway, so that's the measurement of the dew point pressure. Any questions? Huh? What was the problem? No, well, you know, I don't know. The Core Labs people might have equilibrated the cell better so that all of the liquid condensed. Maybe the French lab didn't shake it long enough, so there was some, or maybe there was some contamination in the cell. Maybe it was real. The Core Lab people didn't believe it. They just, you don't know. In all honesty, what we did, we were doing modeling, reservoir modeling, and so we had to run with two cases. Production forecast, assuming that the dew point was much higher, Because what happened is that you started losing barrels, you started losing condensate in the reservoir that didn't produce. So you had one case that was pessimistic, that you had a high dew point, and the other case that was more optimistic was a low dew point. So you had to do a sensitivity on the impact of recovery and recovery rates and economics and everything. You just didn't know. And it was like old data. It was like 12, 15-year-old data when we did this. And so you couldn't go back and drill a well just to collect samples. Now, you guys should, I know it's Friday afternoon, so you probably shouldn't, but I mean, there should be something inside of you saying, why do we have a little mountain here? Why do we have a hill? Why does this thing go up and then come back down? Okay? It's not like throwing a ball in the sky. You know it has to go up and then it comes down. Gravity, everybody grows up with that, right? But why does it go up and then come back down? It's a curious phenomenon. It wasn't known experimentally until the early around the 1930s. It was a curious phenomena. Maybe I've already talked about. Maybe everybody knows the answer. I can't remember what I talked about last year and last week. So, but does anybody have something they want to put forth? First, let's think about what's going on. Okay? When you get some liquid condensing out, what is it saying? Well, which components will tend to form a liquid first? Which components? Will it be the methane?
Heavy.
The very heaviest component. Okay? Okay. If you get liquid coming out in larger and larger quantities, could it be that maybe the very first liquid you see is mainly the very heavy component? A little bit of the other ones, but they basically want to stay home with mom, okay? But then as the pressure drops, the C20 also, some of it has to leave and form liquid. So you're getting more and more of the components forming the liquid as it goes up here. But why doesn't it just keep getting more and more liquid? Huh?
Some kind of equilibrium?
It does have something to do with equilibrium, but everything has to do something with equilibrium, okay? That's the problem. We want to know specifically, what do we know about phase equilibrium? The exercise you've been solving in class, you know? The exercise we've been solving in class, and what we talked about, okay, what quantity says if a component prefers to be in the gas or the liquid phase? What quantity describes the preference of a component to be in a gas to being in a liquid? Yeah, so the K value. And we talked about that being greater than 1 or less than 1. If it's less than 1, that component prefers to be in, remember, up here we had methane.
Gas.
Okay? It always wants to be, if it's greater than 1, it's always having a preference to be in the gas phase. But if it's less than 1, it prefers being in the liquid. Okay? We're talking about the heavy components forming liquid first, not methane. So we'll forget about this methane up here. Okay, and we know that for the heavy components, they all have this shape that looks like this, right? Slope of -1. But then, eventually, they have to turn the corner. We've talked about that. And go up to 1 again, right? Well, in this experiment, we're moving in this direction, right? So if this is some heavy component, pick one you like, C20, right? They all look the same. That may be the value at the dew point. Let's say this is the dew point. It's got a weak preference to be in the liquid phase, right? A relatively weak preference. The monster molecule, C30 plus, drops down like that. You see at the same pressure, this is a log scale, right? This was 0.1. This was C36 plus. This is 0.001. This has got a hell of a lot stronger. That's why it forms in the liquid phase first. Okay? So that's why we would expect this early liquid stuff to be very heavy components, because the K values are much lower. But my question was, why does this go up and then come down? Right? Yeah. So the thing is that C20 has a much stronger preference to be in the liquid. So more of the C20 will go into the liquid as the pressure goes down. But that only goes until this point here. Right? And at this point, if we go to lower pressures, that C20 starts saying, I want to go home. I want to go home to mama. Okay? Back in the gas phase. Same thing's happening for every one of these components. C7's the same way. And even the C30, I'm not quite sure where it'll reach the minimum, but that's pretty nasty looking. Like that. Now the minimum occurs at maybe different pressures for the different components. Okay? But eventually you're going to reach some pressure where all of the components want to start going home again to the gas. And that's what's going to happen. You go to lower and lower pressures, those components want to go back into the gas phase. So kind of this region where it turns, this is basically where the K values of the heavy components turn the corner, turn around. Here, here, and here. Okay, so that's this rhyme and reason to the liquid curve. Okay, so that was just kind of a comment, a general comment, but it does feed back on what we've learned earlier. So remember the K value. If you remember nothing else about K values, and I'm sure many of you can't wait, to get out of this flash calculation mode. But if you remember nothing else other than the fact that if it's bigger than 1, that component has this preference to be in home, in the gas. And if it's less than 1, it has a preference to be in the liquid phase. Okay? That I want you to carry with you, all of you. Okay? So that's basically all of the, I think all of the information about the CCE test for gas and oil systems.